Good morning, everyone. Thank you so much for coming. Today, I would like to talk to you about the procedural encounter system in Horizon Forbidden West. However, you all might be wondering, who is this guy and why is he talking to you? My name is Leszek Szczepański. Hi, everyone. And I've been making games for almost 15 years, which actually is really terrifying to admit because it really feels like I'm just starting out. Over this time, I worked on almost 30 mobile titles and 3 AAA games, most importantly Killzone Shadowfall, Horizon Zero Dawn, and most recently Horizon Forbidden West. Also, I've been extremely interested in procedural content generation in video games, and that passion has seeped into the systems I built for both Horizon games. Today, I'm here to discuss the procedural encounter system, a system that is responsible for presenting the player with opponents while exploring the open world of Horizon Forbidden West. But before we dive in, for those of you who might not be familiar, Horizon Forbidden West is an open-world action role-playing game published by Sony Interactive Entertainment for the PlayStation 4 and PlayStation 5 earlier this year. It is a sequel to the 2017 Horizon Zero Dawn. The game is set in a post-apocalyptic world where giant machines roam the Earth and humanity is no longer the dominant species. In this talk, I'll be discussing the process that went into developing of a procedural encounter system, as well as how it works. However, to put all of this into context, I'll start by briefly discussing procedural content generation systems in general, and follow that up by mentioning some of such systems that are featured in Horizon Forbidden West. First, let's briefly discuss the concept of procedural content generation systems. So, what actually is procedural content generation? The most common definition is algorithmical creation of game content with limited or indirect user input. But to elaborate on this, it means methods of creation of game content either offline during game development or at runtime, meaning during gameplay, that is performed by an algorithm that is only configured by a developer rather than being performed directly by them. Although the first type of procedural content generation that comes to mind, or in Google results for that matter, is generation of terrain, biomes, dungeons, but there's much more to it. To make it slightly easier to discuss, let's divide these kind of systems into 3 categories. But please keep in mind that this categorization is hardly scientific and was made specifically for the purpose of this talk. Let's start with the most obvious type, infinite content generation, infinite gameplay generators. This would be systems that generate content that the player is directly interacting with, things like dungeons, opponents, quests, or loot. These are meant to generate complex content that normally would be created by designers directly, and that is to be replayed over and over. Most notable examples would be the procedurally generated dungeons in NetHack, the procedurally generated narratives in Sunless Seas and Sunless Skies, the randomized weapons in Borderlands, and many more. These usually feature in games that are to be played over and over, or at least for a very long time. The goal is to create a system with an extremely large probability space with as little manual labor as possible. Second category, workflow enhancers, are for generating content which precise details are not relevant. Often used in organic or natural elements like trees or rocks. It doesn't matter where every leaf of grass or pebble is located, as long as they adhere to certain rules, like type, area, or density. This kind of procedural content generation is used mostly on the tool side, offline. However, in some particularly large games, these systems are used as a form of compression. You can generate meshes and other form of data and put them inside your game assets. However, storing a set of rules and having the game do the heavy lifting can save a significant amount of space. Good examples would be the generation of trees and vegetation using the speed tree middleware, placing of grass and foliage that is available on most 3D game engines nowadays, or in general, pretty much anything you can do in Houdini. These serve two purposes. One, to decrease the amount of manual labor required to develop the game, and secondly, for decreasing the amount of game data that needs to be shipped with the game. And finally, simulations. A simulation is an imitative representation of a functioning of a real-world process, behavior, or system over time by means of the functioning of another one, which is a mouthful. Or in much simpler terms, it's one process imitating behavior of another. A lot of game systems can be put in this category, as all modern games have a certain amount of simulation in them. But in the context of procedural content generation, simulations are used in place of manual scripting or direct placing of gameplay elements. The examples most relevant to us would be: in Crusader Kings, wars and conflicts are not predetermined by the designers, but the political simulation of the world ultimately decides about war and peace. In Shadow of Mordor, fights with the enemy tents are not directly designed, but emerge through the interaction between the player and the Nemesis system. In Saints Row and similar games, cars and pedestrians are not manually placed, but are spawned based on rules to make the city feel more natural and dynamic. As before, one of the reasons to use these kind of systems is to have the machine take over some, if not most, of the mundane manual work. But more importantly, these kind of systems can give a game a more natural and dynamic feel, and in many cases facilitate emergent gameplay. Now, let's discuss some of the procedural content generation systems that are featured in Horizon Forbidden West, as well as some of the proposals that ultimately got scrapped or rescoped. This is not an exhaustive list, but these examples are the most relevant to our discussion today. Horizon Forbidden West, as well as Horizon Zero Dawn before it, used a system for procedural placement of vegetation, pickups, various effects, as well as small wildlife. This system uses a number of 2D maps created by the designers, which are later processed in-game at runtime. These 2D maps represent where and how various objects can be placed in the world. The system then dynamically spawns objects in-game using the GPU. If you'd like to know more about this particular system, check out the talk by my colleague Jaap van Mouden from GDC a couple years ago, GPU-based runtime procedural placement in Horizon Zero Dawn. It is not uncommon for open-world RPGs to have some sort of a procedural quest system. A good example is the Radiant system in the good old Elder Scrolls V Skyrim. During the development of Horizon Zero Dawn, a system like that, codenamed Hydra, was proposed as well. But given that the base quest system that we already had was made of clearly defined blocks, it wouldn't be an overwhelming task to add a procedurally generative layer to it. However, given the fully authored nature of Horizon's world and narrative, it didn't really provide any benefits that would fit in with the rest of the game's design. Horizon, at some point, ends. There is a level cap. Therefore, adding a system that would infinitely keep the player in game, although extremely cool, wouldn't provide many benefits to the game at large. A simplified version of it did end up in both games, though. The player is able to generate simple fetch quests for themselves. These don't provide any rewards or XP, but rather are used to keep track of items that are to be gathered for crafting or for trade. If you'd like to learn more about this system, check out my DevGAMM talk from a couple of years ago, Creating Quests in the Open World of Horizon Zero Dawn. During the pre-production of Horizon Forbidden West, we created multiple prototypes of procedurally generated dungeons. We tested multiple designs and multiple implementations. However, ultimately everything got scrapped. For very similar reasons, we already scrapped procedurally generated quests. There just wasn't a good enough reason to keep the player in the game indefinitely. As mentioned before, Horizon is a game that ultimately ends. On top of that, we would need to create a whole new and a rather complex system in order to make this feature work. And to be perfectly honest, we already had quite a bit of things to do. From the very start, we wanted the world of Horizon to feel real and dynamic. Among many things that we did to achieve that, we made sure that the enemies that spawn for the player to fight would change over time and react to various game events. In Horizon Zero Dawn, we had a system which fit that purpose, but ended up needing too much manual labor while not giving us as much variation and reactivity as we wanted. For Horizon Forbidden West, we designed and built a completely new system that was to serve that purpose. That system went through many changes, adjustments, and iterations. Let's discuss that in greater detail. As mentioned before, we needed some sort of a dynamic reactive system for spawning of opponents from the very beginning. The system we had in Horizon Zero Dawn worked as follows. A designer would prepare different combinations of machines that could spawn. That means which ones and in what numbers. Scenes would be manually placed in the world, which could choose to spawn one of those combinations. At runtime, when the player would enter the range of the scene, it would choose one of those combinations at random and spawn the machines. Simple, and although it did do the job, there were issues. First of all, the system required a lot of manual labor to set up. And manual labor is a theme which we'll be repeating over this talk over and over. All of the machine combinations had to be manually prepared and assigned to appropriate scenes. Any control was done through scripting, and those scripts also had to be manually written and maintained. All scene prototypes needed to be manually prepared and maintained as well. Secondly, it wasn't an easy system to tweak. Although design could choose to reinforce certain patterns, there weren't really any specific parameters that we could adjust that would impact what gets spawned and how. That was not only a problem when balancing the game, but that also was extremely cumbersome during optimization. Thirdly, having these collections of scripts, machines, and scene prototypes meant that there was a lot of different data that had to be maintained, a lot of data that could live in different parts of our game content structure, requiring a lot of discipline from the designers not to lose track of all of it. Which leads to the final point. There wasn't really any centralized managing system that would allow to have a quick overview on how all of it is set up. We decided we needed to fundamentally change the workflow and our way of thinking. Instead of looking at individual encounters, we decided to think about machines inhabiting certain areas of the world. These areas, which we called habitats, would be painted on the world map. An encounter would check which machine habitats it overlaps and spawns only those who are available in this area. We wanted for habitats to evolve over time, reacting to the day-night cycle, story progression, and other aspects of the game, going so far as to consider migration patterns based on players' actions in a given area. We wanted not only to spawn machines, but in fact generate whole encounter spaces. Opponents would spawn based on the encounter's location in the world, but also the surrounding geometry. Some aspects of the area would be modified for the encounter as well, adding things like stealth options or takedown possibilities. We wanted a high degree of automation. We wanted to address the amount of manual editing of everything we needed to do so far. The system would analyze the player, the world, the story, and pick the right encounter. Designers would not need to tweak individual parameters, but only the system as a whole. It all sounds beautiful, doesn't it? But as you can imagine, reality quickly kicked in, and these ideals needed to be revised. First of all, we decided to focus solely on spawning machines and other opponents using this system. as in reality that was the only part that needed improving. While having the rest would be nice, we already had good solution for procedural spawning of geometry and the other elements. Therefore, creating a replacement for these additional systems was deemed too expensive and involved for too little benefit. Secondly, it was decided to give designers more control over what and how is being spawned. From an engineering perspective, it would have been fascinating to push the automated nature of the system as far as possible, but ultimately that did not fit with our development philosophy of creating these carefully crafted worlds, going so far as making certain special encounters fully handcrafted. Finally, although we aimed to have everything integrated into our game editor, actually using an external graphics application for drawing the habitats as images and then importing them into the editor was deemed a good balance between the time needed to implement the system versus how much it would decrease our iteration rate. Let's take a look at what the system looked like at its first fully functional iteration. First of all the relevant elements of the system. So first of all, habitat. That's the 2D map painted in the world. Then you have a group, which defines a machine type with all the conditions required for it to spawn. Then you have a category, and this is how we would reference what to spawn. So the designer would specify only heavy machines or scavenging machines instead of specifying which ones exactly. An encounter is what is placed in the game world and what would do the actual spawning. And in order to make things easier, encounters could share settings. And encounter settings specify what is the configuration of a specific set of encounters. And the system is a centralized manager that would contain, and the system is a centralized manager which controls everything, and it also had certain special parameters that we could control. The procedure for the system would be as follows. The player enters the range of the encounter. Then the encounter checks what habitat it is in while checking if they are enabled based on the attached condition. This provides the encounter with a list of all available machine groups at that location. All groups are filtered by the allowed categories for that encounter. That creates the initial list of all possible machines to spawn. Then that list is filtered by all conditions attached to the groups. That filtered list is assigned weights based on the variety parameter of a given encounter, the uniqueness parameter of a system, and what resources the player needs that the machines might provide. The variety parameter of the encounter determines how the likelihood of a given group being chosen decreases with every time it already has been chosen. And that works specifically for a single encounter. The uniqueness parameter in the system works in the same way, but it's a global parameter which works for the whole game. Then, a group is being chosen from that list according to the weights at random, as many times as the settings specify. With every choice, the weights of a list will be adjusted. Finally, from every group, a randomized amount of machines is spawned. And this worked pretty well, kind of. It definitely served its basic purpose. We did have randomized encounters with regional variability. The problem was that the results were very unpredictable. Many different combinations of machines could be spawned, often not making much sense from a gameplay perspective, with no way to narrow them down. A very wide range of amounts of machines could be spawned. You could have 2 or 20, depending on many factors, also without a reasonable way to control it. A very wide range of, another problem was that a large amount of virtually identical habitats needed to be maintained. Because each habitat data structure contained only one machine type, there was a lot of maps, and often they were totally identical. And importantly, it heavily suffered from the most common issue, which is featured in systems that have randomly generated content. And that is that things, although different, were not distinct enough, which each subsequent encounter was different, but it didn't feel different. The system definitely had potential, but we needed numerous iterations. which we did go through. I won't bother you with every change and every adjustment, but ultimately, we came up with this. As you can see, some modifications were made, but the system hasn't changed fundamentally. The most relevant changes were moving a lot of conditional properties from the group to the habitat. Also, having habitats be able to reference multiple groups, while groups be able to reference multiple types of machines. Impact on what kind of resources the machines provide was totally scrapped. And most importantly, adding of a relation data structure which defines which two groups are allowed to go together and how, forming essentially a two-dimensional relation table. The new procedure is as follows. The player enters the range of the encounter. Encounter checks what habitats is in and creates a list. Then that list is filtered by all the conditions attached to the habitats. That provides it with a list of available machine groups at that location. All groups are filtered by the allowed categories for that encounter. Then the filtered groups are looked up in the relation table. From that, all possible pair combinations are created. Each pair combination is assigned a probability weight. Then that probability is modified by the system uniqueness setting to make sure there isn't too much repetition. After that, a pair combination is chosen at random based on assigned weights. And finally, from every group, a randomized amount of machines is spawned. Although the modifications were not major, the improvements were quite significant. The biggest impact had the introduction of a relation table. First of all, it gave designers more direct control on what could spawn. Only two machine types would appear in a single encounter. This also made the whole system more distinct. No more did different encounters have only minor differences between them. And finally, by limiting the possible combination of machines, as well as moving the spawn amounts to a single place, it made it much easier to predict how the system would behave after tweaking. We were pretty happy with this solution. The system met our goals, however, it still wasn't perfect. Even with these modifications, there was a lot of data that needed to be processed, but to address that, we introduced some debug tools. The first one, the habitat viewer, is fairly simple and allowed us to visualize habitats in the world, as well as see the current state of all conditions attached to those habitats. And this works. So the window you see here essentially lists all the habitats, and here you can see the state of all these conditions. So it shows if a habitat has a condition that it only works during certain weather or during certain time of day, it essentially tells whether the weather is fine or the time of day is accurate. And here in the background, that's the view of a game. And these purple boxes that you see are essentially a 3D representation of a 2D map that was painted to define the habitat. It's essentially projected from the top on the height map. This tool was mostly used early in development to make sure all encounters are where they should be and the painted maps translate to the world as we expect them. The second tool, the encounter viewer, allowed us to test and monitor all encounters individually. This one was used extensively by both designers and QA. Most importantly, it showed all relevant data. It showed the list of all encounters in-game. For each encounter, it would show the list of all valid relation table entries for it. It would also visualize the selected encounter area in the world. And every relation table entry, as well as associated groups, would have their probabilities shown, including the current modifiers. Later, we also added features requested by QA, which allowed for quick and extensive testing of the system. Features like teleporting to the selected encounter, resetting the current encounter, and disabling certain elements from the relation table for a selected encounter. These enabled us to test and improve the encounters really quickly without the need to go back to the editor or even to reload the game. And quickly, here what you can see is that there is a list of all encounters up here. That's the relation table entries, which you can disable and enable here. a bunch of controls which allows to reset the encounter, teleport to location, etc. And this is essentially the encounter with all the relevant ranges. It's also worth mentioning that the relation table got fairly big by the end. However, because all of this data existed in a single location, and because we created pretty robust visualization tools, its size was manageable. Ultimately, the system worked pretty well, and it was definitely an improvement over our old setup. It proved so useful that we extended it to implement a feature in which machines could spawn reinforcements during combat. However, not all is perfect. It turned out that while the system was a great fit for big open spaces, it didn't perform that well in small, densely packed ones. In those, we actually needed to add more manually crafted encounters. Although at the moment we are satisfied with how the system works, there are some improvements we are already thinking about. First of all, we'd like to drop the external application step and fully integrate the workflow into our toolset. Secondly, we'd like to revise which properties used for filtering habitats were not used, remove them, and add other ones which might be more useful in the future. Also, it also turned out that the system was still a little bit too difficult to predict when it came to tweaking probabilities, so we were looking into streamlining probability assignment. And finally, because some encounters need to be individually tweaked, something that wasn't really possible in the system, we are looking in ways some encounters could be modified individually beyond what the system allows. So, what did we learn through all of this? First of all, as games are getting bigger and more complex, and that includes everything from single-player hobby projects to gigantic blockbusters, all benefit from some kind of procedural content generation. Both Horizon Zero Dawn and Horizon Forbidden West benefited tremendously from utilizing such systems. There is a plethora of options and methods, and it's good to look into them early on during development. Just make sure you choose the right system for the right type of game. You don't want a very organic, autonomous simulation in a highly authored game, and you don't want to try to create emergent gameplay using laborious scripting. Secondly, probability and randomness are tricky. Human brains are really bad at dealing with it, and that's something we know intimately as game developers when it comes to player behavior, but this is just as important when looking at developers. In all systems that feature some sort of a randomized result, we need to work hard to make it as clear as possible to show what changes to the system might bear what results. Either through simplifying our algorithms and data structures, or through better visualization tools. And finally, working with procedural content generation systems in both Horizon Zero Dawn and Horizon Forbidden West reminded us about one of the hardest to swallow pills of game development. Every system is only as good as it serves the design of the game. To create the best product possible, you can't be afraid to change your assumptions, go back to the drawing board, or even scrap already created systems entirely. Thank you for listening.
Yes, thank you for your lecture. It's very interesting. And right now we coming to the section about the questions. We have microphones in the middle of this hall. So if you have a question, you can come to the microphone and ask. But I will start, because I also have a few questions. And first of all, after all these journeys that you come with experimenting with procedural generation, what you personally thinking? Do you think that personal generation is a way for making games, or maybe it's better to step back and make it all handcrafted, because it's more, you have more control, you have put all design in your handcrafted scenarios?
Yes. No, so the whole idea is that the games are getting bigger, so we will need different kinds of procedural content generation, and that doesn't mean that handcrafted things will not feature anymore. They will just be more complex, and you'll be able to focus on the things that you want to handcraft. Again, you don't want to place every leaf of grass individually, but just say, here's the grass, let's move to something more important. But for some games, you want to push that really hard. Like for systemic games, for games which want to play around with creating worlds, then you want to have procedural content generation as far as possible. So I think that we will have procedural content generation in all games, more and more. It just will be more specialized, depending on what type of game you will be making.
Okay, thank you. And another question, you talk about how you decide how to spawn the machines, but what the machines do after the spawning? They have some random behavior after this?
So that's well, they mostly attack you, duh. But how they exactly behave is a totally different topic. Every machine has a different set of behaviors. Every machine in interaction with other machines also has a different set of behaviors, and that is defined based on machine type, and that is essentially what our whole AI department works on.
But it's possible that you have on the spawn some machines that attack with other machines. So if you are play in stealth, you can observe some behavior and interaction between machines.
So honestly, I don't recall if in Horizon Forbidden West we have these kind of situations. But technically speaking, yeah, they're totally possible. In theory, you could have some bandits spawn along with some machines, and they could have some sort of a combat encounter, which you come in the middle of. But again, I'm not sure if these kind of situations happen in Horizon Forbidden West.
Okay, and another question is more about some vision of the future. What are you thinking about machine learning for this process?
So machine learning is interesting because people say AI and immediately think machine learning, but AI is a very, very wide topic. My personal opinion is that it will be a big feature and become a bigger feature of game development, but not during gameplay, but during content creation. Again, making it less laborious to do the simple stuff, that's what the machine can do, and machine learning can make that much easier. But during like the game itself, I don't think the machine learning methods are efficient enough to be able to put in the game, at least currently.
Okay, I understand. It sounds from your lecture that you're saying that it's very unpredictable things you have with rules that you understand how it works, and if you're working with machine learning, it's much more unpredictable. People, okay, the first questions.
Hi, my name is Michael, board game in Vilnius. I'm happy to attend another lecture of Guerrilla Games. I was in San Francisco. It was very interesting lecture. Your worlds became bigger, more complicated. You have more systems than the previous game has. But there is a lot of content. There is a lot of systems. Are your quality engineers testing all manually, or you have some automated tests or some machine learning tests? Thanks.
So as far as I know, we don't use any machine learning in testing, but we have a substantial QA department which have their own procedures, which I'm not that familiar with, so I won't go too deeply, but we have people who do QA manually, but we also have automated testing. Manual automated testing is mostly related to the stability of the build. So we have units tests and these kind of things. We test certain gameplay features in an automated way as well, but for that we mostly rely on QA.
Thank you.
Thank you.
Hey, yeah, my name is Masha. I have actually two questions. The first one was, I think I also met rebels during like my gameplay. Were rebels also part of random encounters, or like it was only for machines?
No, so the system was designed for machines,
Yeah.
but it's able to spawn pretty much any kind of opponent.
Yeah, so it just, I was like, I want to ask whether also random or not. Okay. Yeah, the second question what I had is, how did you determine what player needs at the moment? Because you said that it's also part of the system. Like you
So-
measure it somehow? Because I remember that I had like 30 quests at the same time with crafts and with also the stuff. And how did you determine what I'm going to do next?
So the thing is that we wanted to do that initially, but although technically that's not that big of a deal because you essentially go through the quest list, see which objectives require what resources, and you already have a set of data you can work on. From a gameplay side, that is so easy to exploit that we decided not to do that at all. So what would happen is that by starting certain quests or even doing certain jobs for yourself, you could manipulate what machines spawn, and we didn't want to have that.
Yeah, like do safe scamming, right? And down.
Sorry?
Oh, no. Never mind. I was talking with myself.
Okay. Thank you.
Yeah, thank you too.
Hi, my name is Sergey. Thank you for talk. And I have a question, more technical one, like for the random generator. Have you used just normal random generation or like uniform? Are there like any parameters that are more likely to happen and some are less likely? Do you manage it somehow, or you just like every other encounter is equally possible?
So, if I understand your question correctly, essentially most of the things that are chosen at random were based on weights. So, if you essentially create this final list of machines, given, for example, their history, we would change what would the next machine spawn. So, if, for example, you would have machine A spawn previously, it would have a lower chance of spawning again.
I see. So it's dynamically adjusted.
Dynamically adjusted, but most importantly, the painted habitats had an impact. So, as I said, we have these 2D maps which you paint in the world, and say the northern area are these robots, and the southern area are another kind of robots.
And during testing, did you find out that your algorithm produced some really bizarre output for randomness? So it was, I know, funny or unplayable.
Well,
any examples?
If you work with anything randomly generated, is that you get bizarre results. That's a given. But that's why we introduced that relation table to limit that. Because initially it was very random. So you would have an encounter with 5 different types of robots, which didn't make any sense. And that that did what we thought we needed, but it was just too random. We didn't have anything totally bizarre, like spawning 15 of largest robots or something like this. But we did have like always too often like a weird mishmash of robots, which gameplay-wise just wasn't fun. That's why we introduced this another layer, which limited only to pairs, and we defined which pairs could spawn anywhere.
Okay, see you. Thank you.
Thank you.
Yeah, hello. Thank you for the talk. It was very interesting. I had a question more in the lines, not exactly encounters, but in general procedural generation. You said that one of the reasons why it's very beneficial to use procedural generation is the saving of space, which is obviously true, and it's always but it's always a trade-off between space and computing power. So how would you balance this relation? What do you believe, how much of a game is good to move to procedural generation, and when does that become like a bottleneck in the sense of efficiency?
So, I mean, I wish I would have a silver bullet for you, but I think it depends on the scale of a game you're making. I think I would have 2 different sort of procedures. If you know from the start that you're making a huge game, I would move as much possible into procedural generation from the very start. And then if it proves a problem with performance, I would then think about what to do with this. If you're going from the other way and you know that your game will be kind of small scale, then just don't bother with procedural generation, at least at runtime. And then if the game just inflates in size, then start thinking, okay, maybe I can decrease the size of the package by procedurally generating at runtime this bit or this bit. So I would kind of converge from different sides depending on the size of the game.
Okay, thank you. And on a similar note, if we're talking about organic textures, in that sense, when in the game, are they pre-generated and then as a development process and made and then put into the game, or are they actually generated in runtime?
You're asking about textures?
Yeah, like rocks, foliage, whatever, you know, like, because that's an often used, you know, like another place used for procedural generation.
So I can just give you a very rough overview of this. Because again, if you want to do like a deep dive, a colleague of mine who worked on the system did like a very extensive talk a couple years ago. But essentially, if I remember correctly, everything that gets spawned itself is predefined. It's only the GPU which populates the world on what gets spawned where. And if I also recall correctly, it's very stable. So the tree which will get spawned through that system spawns always in the same place. The grass might be, for example, a little bit different.
Yeah, so, you know, obviously seed generation then, I assume, you know.
Yeah.
Okay, thank you.
Thank you.
Okay, maybe someone else. Okay.
Hey there. So you actually mentioned the external software for the drawing of the habitats, for the weights of the encounters. So do you actually know which software did the designers use for that?
It's Photoshop.
Ah.
Yeah, essentially the way it works is we just draw all these. We have like a background layer with the world map. And on top of that background layer, we have multiple layers for each habitat. And we have a script which exports into PNG files. And these PNG files are then, through a different script, imported back into game and processed. The only thing we really needed to do is to make sure that the resolution of that image meets certain parameters that are required in game. So you know that a pixel is this amount of meters in game. But yeah, it's Photoshop.
So the images also probably were tiled based on chunks in the world, right?
Sorry?
I mean, each image probably represented each chunk of the world. So like you had multiple ones for the whole map.
No. So each image represented a single habitat.
Ah.
But it was the whole world. So you painted like on the world map.
Thanks.
Thank you.
One more question from me. I'm also thinking about this situation when the game designers need to deal with something unpredictable. And maybe some recommendation for game designers, because of course, if I'm making the games, I want to control everything, but when you're working with the procedural generation, it's not possible, and you need to have some tolerance to unpredictability. So how is deal in your
Well, I would suggest just focus on the things that are really relevant, because you can have control over everything, but so what? It doesn't really matter where certain elements are placed. So if you're designing a system, think about which parts of the system actually are player-facing and have an impact on the player experience. And the bits which don't, just let the machine do the magic. That's my suggestion.
Okay, thank you. Okay, so if you have no question, then we're finished. Thank you.
Awesome, thank you very much.